So, hello, am I starting?
Maybe I'll do a quick intro. Yeah.
Okay, sure.
Okay. Hi, everyone, and welcome to our new series of talks called Expert Exchange. Sorry for the few minutes of delay here. So, the goal of this talk is for us to connect with leading researchers and power users of PyTorch. I'm Supriya Rao, and I work on PyTorch, and we're really excited to kick off this series today. So, at PyTorch, we are really committed to staying at the forefront of cutting edge research and innovation. And what better way to do that than to connect directly with experts themselves? So, through this series, we really hope to learn about the latest advancements in AI and share those insights with the wider PyTorch community, and at the same time, understand how PyTorch is being used by the research community. So, each session is going to be live streamed on our PyTorch YouTube channel. So, you can either watch it live or tune in later and learn from this, hopefully. So, without further ado, we want to get started with our very first guest, Muyang Lee from the MIT Han Lab, who will be talking today about sparse and distributed inference for generative AI models. So, Muyang, feel free to take it away from here.
Yeah. So, hello, everyone. I'm Muyan Li, and I am very glad to give a presentation here. So, my presentation's title is Efficient Generative Models from Sparse to Distributed Inference. So, firstly, let me briefly introduce myself. I'm a rising second year PhD student at MIT, advised by Professor Song Han. And previously, I was a master's student at Carnegie Mellon, advised by Professor Junyuan Zhu, and I obtained my bachelor's degree at SJTU. So my research interest lies in the intersection of machine learning, system, and computer graphics. And I'm currently working on building efficient and hardware-friendly generative models with its applications in computer vision and graphics. So let's begin. AI-generated content, also known as AIGC, has recently gained a lot of attention and produced remarkable results. So the examples are like Adobe's Firefly and Midjourney. And recently, OpenAI's Sora has further pushed the boundary to video generation, and the advancement of generative models played a vital role in achieving such milestones. A few years ago, GANs, which are neural networks composed of a generator and a discriminator, were introduced. These networks work together to generate um, realistic images by competing against each other. And the recent development of diffusion models has further expanded the boundaries of AIGC. These models define a forward process to add noise to diffuse a clear image to pure noise. And then a network is trained to learn the reverse distribution to reconstruct the image back from the pure noise. And these models have given rise to numerous image synthesis and editing applications. For example, GAN can convert the semantic maps to photorealistic images. And SD Edit can edit real images with your painting strokes. However, these models are very computationally expensive. For example, a single step of recent Flux 1 requires 36 times more computation than recognition VITH, and still 3 times more computation than Llama 3 AB. The video model, called Video X, even requires a magnitude of order more computation. Moreover, the computation will scales super quadratically with the resolution. So such prohibitive computation amounts presents a tremendous barrier for the applications of the generative models. So back into 2020, I began my research journey on building efficient GAN architectures with a paper called GAN compression. It was accepted by CVPR 2022 and TPAMI 2021, and has also received 1.1K stars on GitHub. And it is a general purpose GAN compression framework for conditional GANs, with distillation and neural architecture search. And it reduces the computations of different GAN models by 9 to 21 times. And on the right-hand side, we show a demo of CycleGAN on Jetson Xavier. And you can see our GAN compressions achieves a 3 times faster FPS with better FID, which implies better quality. And we also deliver an interactive pixel-to-pixel demo to convert the edges to shoes on Jetson Nano. And you can see on the right-hand side, the eraser is more smooth, and it delivers a 2.5 times speed up compared to the left example, the original model. So through the previous interactive demo and the current video, we can see that content creators often edit the images very gradually after finishing the background. And they only update a small regions of the image at a time. Despite this fact, recent generative models tend to synthesize the entire image, even for minor edits. For example, Stable Diffusion requires 1800 Gmax for 40 steps given a user input to generate the image. Sorry. And then the user adds a moon on the sky, which only occupies about 1.7% pixels. Unfortunately, vanilla Stable Diffusion requires another 1800 Gmax per step to resynthesize the entire image. And this definitely wastes too much computation, since only the moon has changed. In fact, the feature maps stay almost the same at the unedited regions. So these observations motivates our paper Efficient Spatially Sparse Inference for Conditional GANs and Diffusion Models, which was accepted by NeurIPS 2022 and TPAMI 2023. So our key idea is very simple. Seeing when you do the original image inference, you can cache the feature maps of the previous edits. And then when you add the moon on the sky, when the edit is done, we reuse the cached feature maps and only perform computation to the newly edited regions, like the moon. And it reduces the computation by 8 times in this example. So our overall philosophy is that we switch the previous mode of local edits, global computation, to local edits, local computation. In addition to the spatially sparse inference algorithm we mentioned before, we further implement a Sparse Incremental Generative Engine, SIGE, to translate the theoretical computation reduction to measure speedups on different hardwares like NVIDIA's GPUs and Apple's chip. So our SIGE uses a tiling-based sparse convolution algorithm. For each convolution in the model, we just wrap it into a SIGE-conv. And here AL is the input activation, and FL is the else layer, convolution layer, and FLAL is the output activations. And we suppose that the original image feature has already been pre-computed and cached. And when user finish his editing, we can compute a difference mask to locate the edited regions like these clouds in the example. And we downsample the mask to different resolutions, and for each resolution, we divide the mask into small blocks and reduce it to active indices, which index the edited blocks, namely the clouds. After we get the edited input activations at the layer L, we use the active indices to gather the edited blocks along the batch dimension. Like we fetch the clouds from the skies and then feed these clouds into the convolutions to get the edited output blocks. Since we have already fetched the clouds from the sky, all we need to do is that we need a scatter operator to put the clouds back into the skies, like as in the original activations. And we perform this kind of behavior layer by layer, and then we can get the final outputs. So that's the main algorithm of tiling-based sparse convolution. Besides convolution, we also optimize the attention layers, which is also very computationally expensive in diffusion models. So here's a standard pipeline of the attention. And you have the edited activations, and you first pass it into the QKV-conf, and get the query keys and values. And you C prime here means the hidden dimension. And you first use batch matrix multiplying the query and keys to get the attention map. And you multiply this attention map with the value to get the output. I guess everyone is very familiar with the attention pipeline. And the problem here is that if you want to generate a 1K by 512 image, your attention map can be 8K by 8K for stable diffusion, and which is really giant. However, we still find that even after the self-attention layer, the feature maps are very similar at the unedited regions. So this enlightens us to only recompute the output of the edited tokens, the edited query tokens. So in the SIGE attention block, we first use a gather to prune the unedited tokens and only preserve the edited ones. So here, N denotes the number of edited blocks, and H and W denote the height and width of the block. For keys and values, we scatter them back, but there's no such an operation for the query tokens. And after the BMM and softmax, we scatter the edited query results back into the original outputs to get the final output. So here we transform our self-attention layers to a cross-attention layers. And the computation and the attention map size is proportional to your edited ratio, so we can reduce the computation proportionally. And we also have some other kinds of optimizations, such as the normalization layer removal and kernel fusion, and you can refer to our papers for more details. Here we show some qualitative results here on stable diffusion. So the first task is image inpainting, and we mask out 11% of regions, and with the text prompt, a photograph of a horse on a grassland. And our method can reduce 3.6 times computation and achieve almost 4 times speedups on 3090 with no quality degradation. So you can see these two horses are almost the same. The other task is image-to-image translation. This is the original image and the edited image. I add a coconut tree, which only occupies about 2.9% pixels, and this drawing is made by me. And the prompt is a fantasy beach landscape trending on ArtStation. And you can see our method can achieve 5 times computation reduction and almost 5 times speedups on 3090. In addition to diffusion models, our method can also work for other generative models like GAN. So it can also work on current efforts of few-step diffusion models. For example, it reduces 18 times computation for GAN. And it is also complementary with the model compression methods like GAN compression, which we mentioned before. And when combined together, it reduces the computation by 50 times. Regarding efficiency, SIGE achieves a 4 times speed up on GAN on 3090 and 14 times speed ups on M1 Pro CPU. When combined with GAN compression, it further achieves a 38 times speed up on Apple M1 Pro CPU. And here we also build an interactive demo of DDPM's SD edit on my own MacBook Pro's GPU, M1 GPU, I think it is. And our method only resynthesizes the edited cloud, so it is really fast. It is doing the incremental inference. And I think PyTorch helps a lot in our project. So we use PyTorch as our framework to deploy our models, since it can seamlessly support and run my customized C++, CUDA, and MPS extensions. But we also met some minor issues during the project, like when deploying the demo. First, at that moment, I think Apple just released their MPS backends, and there are limited resources for the backend and the extension. So I spent a lot of time exploring this, and the MPS naive PyTorch operations often also had some bugs at that moment. I guess it is just because I'm using a preview versions of the PyTorch, not that stable. Yeah. So recent efforts to accelerate diffusion models is like focus on mainly on two approaches. Like the first one is reducing the sampling steps, like the progressive distillations. And the other is like we optimize the model inference, like the aforementioned SIGE. As the computational resources grow rapidly, leveraging multiple GPUs to accelerate inference is also very appealing. So for example, large language models have already harnessed the tensor parallelisms across GPUs to significantly reduce the latency. But however, for diffusion models, when generating a single image, typically only one GPU is involved. And it is very hard to parallelize different time steps due to its sequential nature. And techniques like tensor parallelisms is less suitable here due to the large activation size of diffusion models. And as the communication cost may outweigh the savings from the parallel processing. So how to parallelize diffusion models? Motivated by this, we invented DistriFusion, distributed parallel inference for high-resolution diffusion models. And it has been accepted by CVPR 2024 as a highlight paper. So a naive approach to distributedly run the diffusion models would be divide the image into several patches and designing each patch for different device for generation. And this method allows for independent and parallel operations across the devices, but the problem is that it suffers from severe fragmentation issues due to the lack of interactions between the patches. So you can see here, it generates two astronauts. However, if you want to add the interactions, there will be excessive synchronization cost again, offsetting the benefits from the parallel processing, even though the image quality is well preserved. But in fact, the inputs across adjacent time steps in the diffusion models are also very similar. So this enlightens us to, so inspired by this, we propose a new parallelism paradigm called Displaced Patch Parallelism, which reuses the pre-computed activations from the previous step to provide the global context and the patch interactions for the current step. In this way, the communication can be overlapped by the computation, and the overhead can be hidden. And we further implement such a system called with the asynchronous communication called DistriFusion. So when we get the input of the time step t, we first split it into two patches like what we did before. And then we feed them into the model layer by layer. At layer L, each device will have n activation patches. We first use an asynchronous OR gather to concat and cache the features for the next step. And note that this communication is overlapped with the computation. So the current step should have already received the stale activations from the previous step. We then scatter the activation patches back into the stale activation features. And we only perform the computation sparsely at the fresh regions, like this fresh. This is the sparse operation, and this is the sparse regions. And specifically, if FL is a convolution, linear or cross attention layer, we apply the operator exclusively to the fresh regions, like what we since this is elementary-wise operator, so we do not need to care about the stale regions. And if FL is a self-attention layer, we transform this self-attention into a cross-attention, using the fresh regions to attend to the whole feature maps, like what we did in SIGE. And finally, we can get the predicted noise and update the noisy inputs and get xt minus one, and repeat this process for the following steps and get the final outputs. And you can refer to our papers for more details. And here we show the efficiency results of DistriFusion. So in the original 1K resolution, we achieve 1.5 times speedups and 2.8 times speedups on A and 8 A100 respectively. And this is mainly because the devices are underutilized, since the SDXL is not a quite large model. And so to maximize the device usage, we further scale up the resolution to 2K and 4K. So specifically for 4K resolution, DistriFusion reduces the latency by 6 times with 8 A100s. And note that these results are benchmarked by the very naive PyTorch inference, and with more advanced compilers or with torch.compile, we anticipate even higher GPU utilization and consequently more pronounced speedups. And here we show our quality results. These are the original images of the SDXL, and using the naive parallelism can achieve a 3.9 times speedups. But images have noticeable duplicated subjects here. And our DistriFusion can well preserve the quality with no visual differences and deliver 3 times speedups. Yeah, And I also want to shout out my thanks to the PyTorch community. Like PyTorch also helps a lot in our project, this project again. So it is very easy to implement the communication at PyTorch in PyTorch at the Python level, and it also natively supports the qdot-graph to optimize out the kernel calling overhead. Without qdot-graph, I think our distribution speed up is mainly bottlenecked by the communication kernel calling. But we still meet some minor issues when doing this project. Like we cannot further optimize the model's performance with torch.compile, as we have the asynchronous communication, and previously async communication is not that compatible with the torch.compile. And we also observe that our async communication will slow down the computation a little bit, as it will also take out some computing resources on the GPU, namely the SM. And I think this is a well-known NACO issues, and it will slow down the performance by about 10%. And the last one is that we also observe the Q.OOM issues when generating a really high resolution image, like as shown in the figure below. The memory demands for the standard PyTorch convolutions will dramatically improve when the input parameter size reaches 1 billion parameters. And this may be because of the CUDN or Catalyst implementation, and maybe not because of the PyTorch framework. And that's all for my today's presentation, and I'd like to thank all my collaborators for their help. And thank you very much for your listening.
Thank you very much, Yang. This was great. It was really nice to hear about the research and also how PyTorch helped and where we can do better. So thanks for sharing the feedback. We also have Kay and Les from the PyTorch team here in case I'm opening the floor for any questions and discussions now.
Mm-hmm.
Actually, I wanted to mention something that we do have currently bubbling up, which is you were talking about the async communications being slow. So for async TP, which is a new feature for PyTorch distributed, Ifu's actually written some new zero copy collectives. So they're not actually using nickel. So it's basically a symmetric memory, direct memory access, GPU to GPU. So that should give you, and it's funny you said 10% because on average we see about a 10% speed up doing that. So we don't actually have an all gather yet is the one bottleneck, but that should be coming in the next month or so. So
that's really
very well be addressed exactly what you mentioned here.
Exciting. So. Yeah. We are very annoyed about the 10% performance loss since this is the main overhead of our algorithm.
Yeah, that's exactly what it was about, was speeding up for that aspect. Now that's specific to within a node because we're relying on NV switch there. And also I should say H100 is the other caveat to that. So
Yeah. Thanks for your help.
Oh, I think you're muted, Ka.
Thanks, Lex. Yeah, nice talk, Muyan. To follow up on the slowdown, right? So I wonder if that's due to a sharing of memory channel between the all-gather communication kernel and the computation kernel.
Previously, we just used I think the dist dot altogether and passed the async flag. And I run a very toy example, and I found when I was doing the communication and at the same time I'm computing a very large gem.
Yeah.
And I found the gem's performance will decrease about 10%.
Right.
Even though the communication is indeed overlapped with the computation.
I see. Okay. We can follow up with say Nicole team or NVIDIA to investigate the reason. But one of our guesses, that there's increased memory pressure, right, when both kernels want to access data, and hence they slow down each other. And second question from PyTorch point of view. So what kind of distributed feature do you think will help your framework, your image generation framework, be more efficient, be easier to program?
I think currently, yeah, it is very easy to program. But I also observe some undefined operators. I'm not sure if this is a bug of my program or some undefined operator in PyTorch. I guess it is mainly because of my side. And currently, I think PyTorch is very easy to use, and I'm thinking about if I can combine with the torch.combine and integrate my async communication into the torch.combine, since I also want to optimize my computation kernels, not only my communication.
Right.
To better exploit the GPU usage.
So got it. So you want improvement in the composability between torch.compile and some advanced communication calling.
Yeah, I'm not sure if torch.combine currently supports the multiple GPU models, like if you have communication between the GPUs and this communication is asynchronous, and I'm not sure if torch.combine can optimize it.
With between the communication blocks, it can. Hopefully in about 2 to 3 more months, we'll have full traceability for Torch compile, meaning it will actually trace through and have a full single graph even with the communication collectives. Right now, it'll actually break and you'll get a fusion between each communication set, basically.
Yeah. And I also found that qdot-graph is a very helpful feature. Like it can optimize lots of kernel coding overheads in the communication. So without the qdot-graph, I think DistriFusion is even slower than the single GPU model. But with qdot-graph, the performance will improve dramatically, like multiple times. Yeah, but I think currently the qdot-graph's API is a little bit complex, and I spent maybe several days to figure it out how to implement such a features. But I think it is still a very good job.
So yeah, I think we have a question from the comments on from Mark. Does this work on quantized models?
Yeah, currently we have some ongoing projects on quantized models, quantized diffusion models, and I think we will combine the quantization with our distributed method and finally deliver more complete systems for the community and for the industry. I think, yeah.
Yeah, second question is, can you please elaborate how the new torch.distributed collectives address the asynchronical slowdown?
Currently, I have no idea how to figure out how to resolve that issues, but we do observe that. I think previously, I have already read a paper. It said that you can hack the system code. I think it is not addressed at the PyTorch level. It is at a more bottom level, like to use the remote GPU access instead of using nickel to bypass this issue.
Yeah, I think this question was referring to what Les mentioned, the async CUDA memory collective. That was a
zero copy collective or symmetric memory, however you want to term it. But basically, what the delta here is that it's basically opening up a buffer on every single GPU, and they're doing direct communication GPU to GPU, and so that's basically your speed up. Like I said, there's some limitations to it. It's assuming H100 because it relies on NV switch for that direct access. Secondarily, it is currently only operatable within single node. It doesn't actually span across nodes. So those are basically, if you look in Torch Titan, they're implemented with the async TP. And like I said, the one caveat here is we don't have all gather yet, but that is in the works. So basically, it actually addresses sort of, I think you guys were talking about the SM contention. As it's doing compute, as doing collective, it eliminates some of that contention as well as also where it gets the speed up.
Mm-hmm.
I'm not familiar with NVIDIA Sharp, so I don't know.
I'm also familiar with that.
Short answer.
So if by NVIDIA Sharp you're referring to the network shop, then it probably doesn't because it's intranode operation. But if by NVIDIA Shop you're referring to the NV switch shop, there's a potential that this kind of symmetric memory between GPUs can also utilize that functionality.
It does rely on NV switch, so in that sense, yes. Actually, Myung, I was just curious, have you actually tested across node? And specifically, I mean, I don't think that'll work well at all in terms of speed for A100, but with H100s, we have a much better cross node bandwidth. And I'm just curious for scaling to even larger images, is that something you had a chance to look at?
Currently, our experiments are mainly conducted at a scale of one node, because previously the diffusion models are not as large as the large language model. Like it only has about 2.6 times parameters, and I anticipate 8 GPUs is already an extreme case.
Okay, gotcha.
Okay. Any more questions, Les or Kay?
Oh, yeah, actually, I have one more question. So if I understand the diffusion workflow correctly, there will be a number of steps of calling the UNet. Do you think about another parallelism scenario where you put, say, you have 16 UNets in total, you put first 8 UNets in one GPU and then the second 8 UNet steps in another GPU. And then obviously, if you only have one image to generate, this is still a sequential operation.
Yeah, this is a pipeline. This is some pipeline.
Right. So, but if you have like in a service scenario, you have multiple requests, right? Like you have a lot of batch of data, then potentially we can pipeline all the workload while request 1 is in the second GPU, then request 2 is in the first GPU.
I think this is feasible, and I think there are already some works exploring this, like the string diffusion. But string diffusion is not looking at it's not mainly handling the distributed scenario, and it is only focusing on the single GPU. But the idea is very like what you said just now. Like this is some streaming issue and the pipeline. Like you first when you have some requests and your first GPU is idle, right?
Right, exactly. So if that applies, Torch today also have a Torch.distributed pipelining package that can help you easily pipeline your model in an abstracted manner, such that one single model automatically gets separated onto different devices without you having to go into the detail to write, say, or gather or send receive calls.
Well, I can find the paper. Okay, I don't know how can I share the links, and I think you just need to maybe Google these papers. You can stay updated with our projects, and we will just post the newest news in our websites once we had it.
Okay, maybe we can share the slides.
Yeah, sure. I can also share the slides if you want.
Yeah, that'd be great. All right. I think, I don't see any more questions from the comments. So want to wrap things up here. Thank you, Moyang Lee, for...
Where should I update the slides, like via email, or is there a dedicated website to do that?
I think we can follow up and we can update like the video description of this talk with slides and any other details you want to include about the project.
Okay. Yeah, thanks for your invitation. It's very exciting to present here.
Yeah, it's really fascinating to see how PyTorch is being used externally, and really value these conversations with research labs. So I guess with that we can wrap up the first session of our Expert Exchange series, and we hope you all have enjoyed it, and we'll see you all at the next one. Thank you.
Okay, have a good day.